Hold on 1 second. Hello? Okay, it looks like we've got a few people here. So I'm going to go ahead and start. Let me just change my lighting a little bit. I'll be right with you. That should make it a little bit better. What I'd like to do tonight, for those of you who joined us, is we're going to go through the main items in the study guide, and wanted to give you one, sort of first go over what I expect, and then second of all, give you a chance to ask questions. I believe you should have a question area on the side. Let me just see. Oh, features disabled. Okay, since that's disabled, I am going to do it a different way. Give me one moment. So the first thing I'd like to do is to go through the study guide, and I can do that by sharing this, I believe. The main things that we want to cover are, let's start out with the software development process. One of the things we want to think about are what activities are part of the software development process, and that would include things like requirements gathering, analysis, model building, the design activity and testing, and then there are the software development management activities, and then there, which would include the process itself, and then for the 4+1 view of architecture, there's the notion of the use case model that couples the logical model, the development model, process model, and deployment model. For UML modeling, in a use case diagram, remember that a use case model includes the use case diagram plus the description of the use cases themselves. And so the model, the use case model itself, if somebody says create a use case model for a particular system, you may start out and create use case diagrams that would include the different use cases, the actors and their relationships. And then we also have the descriptions of them, including the exceptions that go along with them. Class diagrams and associations. Class diagrams include which classes exist, usually in the analysis and design model, what their associations are, for example, like the ones we looked at today, and then the nature of their associations. But to really understand use cases, we often sketch out object diagrams in scenarios so we can see what happens when specific instances work together to accomplish some goal, and we know that those objects are a member of some class. So we see in those object diagrams which associations we have, what links we have, and then the communication or interaction diagrams show us how the objects interact with each other in order to accomplish a particular use case. So when we look at requirements, what we're really doing is thinking through a series of different use cases. And when we look at those use cases, we're using that as a means of gathering requirements in an organized fashion. What happens is, and as you saw in the requirements for the timing system, is that the requirements are not always well organized. The way customers typically write requirements is they're thinking of different scenarios, and they're thinking through how something interacts with each other, and they're going through specific scenarios and describing how they want that system to work. They also tend to make a lot of assumptions, and one of the things we purposely done in that first requirements document was to leave out some information, which means you have to go back and ask questions of the client in order to fill out those models. And so as we go through requirements, one of the things that we see is that we create use case models which list out the actors, the use cases themselves. We identify the system boundary. In other words, what's in the system, what's not in the system. That's very important. That's not part of my charge versus what's inside the system, which is. And then create scenarios that help us identify what specific objects are going to be needed, what classes they belong to within the domain, and how they interact. And that's going to help us identify what behaviors they actually need. And so as we start to do that, we start to assign these responsibilities to the different objects in the system. Now, what that means is that we're allowing ourselves to go through and trace all of the required behavior in the system. And as part of that requirements modeling, we're modeling both the functional and the non-functional requirements in the system. Now, typically, the functional requirements are captured in those use cases, but non-functional specifications come up, typically having to do with performance, how fast something is going to have to happen, or how reliable it has to be, or maybe scalability. How big does the system need to be? Does it need to handle thousands of users, 2 users, millions of users? And that's going to help us make architectural decisions later on that we haven't really talked about yet. So when we look at functional requirements, they tend to specify what needs to happen in the system. In other words, what result is required. And a non-functional requirement tends to tell us how that's going to be accomplished in terms of how, you know, how fast or how slowly, sort of like an adverb would be in English. So since the for some reason the Q&A is not enabled, and I don't know how to change that at this moment. You can also text me any questions you have or email them. You can text them to 414-899-8269 and 414-899-8269, and that should work in there. The next thing in that I want to make sure people know is in testing, there's the difference between test plans and test cases. Test plans are going to tell you, what am I looking to test and what do I need to do the test? A test case is specific about, this test has an expected result, here's the actual result, here's the difference. In other words, whether it succeeded or not. And so it's important to know the difference between those. Test plans typically will have many test cases associated with them. And those test cases are going to test a lot of the boundary values. And when we look at boundary values, that was a pretty large discussion we had. It's true for both black box and white box testing. The boundary value analysis keeps us from having to test all of the possible input data and measuring all the possible output, especially when there might be an indefinite or infinite range of input values. They're not just a number of discrete values. So what boundary value analysis does is it allows us to constrain the set of test cases that are needed to be included in a test plan for a particular feature or component or subsystem. And you should know the difference between black box testing and white box testing and why we make that difference. You'll also want to know the discussion we had on boundary value analysis, which is where we can look for those, how to identify particular types of boundary conditions or edge conditions, what different types of stress testing are, which is in the slides and also in the book. For white box testing, the basis path or the cyclomatic number is very useful, and you'll want to know how to calculate that. And the reason that we want to know how to calculate the cyclomatic number is that it gives us an idea of how complicated that component is going to be to test. And that's going to tell us a lot about the number of test cases that we have to have, and subsequently the boundary value conditions that we need to worry about. And that's going to lead us to this sort of flow graph. Here's all the possible paths through something. And that's going to help us make sure that we have appropriate branch and method coverage, statement coverage. And of course, we want appropriate method coverage. So you want to know the difference between method coverage and statement coverage. Method coverage is, let's make sure I test all of the methods in a reasonable order for that component. In other words, if there's a specific protocol that I have to use, that I observe that. And for statement and branch coverage, we want to make sure that, first of all, we're forcing all the branches with our cyclomatic test, our flow graph, and that we are covering all of the statements in the system. In the methods within that component. So there's quite a bit on testing there. And this is primarily because in a well-engineered system, we're not just trying to test out the main use cases and making sure that everything sort of usually works. We're thinking primarily about boundary value conditions. If you think about, for example, if anybody's ever taken flight lessons to learn how to fly a plane, one of the things that happens there is, in one day they teach you how to fly the plane normally, normal conditions. All of the rest of your flight lesson has to do with what happens in an exception. And the same is true in testing the software. we assume that it kind of works in the normal conditions, but we're trying to test all these possible exceptions because we don't want the software to error out in those different situations. And not surprisingly, it can be a little tedious, but there it is. So the testing, test plans, test cases, and then the difference between black box and white box testing, boundary value analysis, and making sure that we have method coverage, statement coverage, branching coverage, and using cyclomatic numbers to help us figure out how many different cases we're going to have to work with. And then in design patterns, which we did today, and I have to put that up. I will do that right now as we're doing this. As we went through the different design patterns, we started out with a few, and we're going to do some more later, but we looked at observer, memento, and command as a pattern. And we went through command as a pattern a little bit quickly, but I think it's for the most part pretty clear how that works. We're then going to talk about the model view controller pattern a little bit later on, and we'll be looking at the patterns for dealing with interfaces when we talk about interfaces. I'm just going to, while I'm right here, I am going to go and under patterns, upload this file for you so you have it. And this is the slides from today. So that should be up on D2L now, the slides from today. So for this first test, it's pretty straightforward. It's mostly the software development process, basic UML, and by basic UML we mean class, object, interaction diagrams, and use case models. And then the process of gathering requirements and creating a requirements model that's basically your use case model, plus the analysis model, which says what things exist in here. And what we're trying to do in analysis is understand what the system needs to do. And then in design, we're turning the other direction, saying, how do I make it do that? And so in design, we talked a fair amount, we talked a fair amount about the process of creating more detailed versions of the interactions, those use cases, to understand what behaviors we need in the system. And so we looked at interaction diagrams as a way of decomposing a particular use case, allocating behaviors to the different objects, and now deciding what those responsibilities need to be. And then we talked a little bit about subsystems and how the fact that a given subsystem may in fact have several different objects within it, but that we have one class that acts as the interface to it and delegates behaviors to the other classes within that component, or within that subsystem. And that is actually a little bit of an introduction to this idea later on, where we use an adapter pattern that says, well, I'm going to give you an interface. Here's the things that this subsystem can do, even though internally I've partitioned it into smaller objects. And we saw that in the one set of slides where we were in the compiler, where we said, oh, well, we have the parser and the lexical analyzer and the parse tree and the dictionary, etc. But in the end, it had a very simple interface that allowed you to simply compile some code. Let's see. What else do we have? Oh, I know one way I can do this. So the once again, if you have any questions, you can text those to 414-899-8269, and I should be able to get those right here, and I can answer any of those. And somebody wasn't letting me screen share this. Okay. So I think one of the things that's come up in a number of discussions with people is in the requirements gathering that when you create use cases, there's really two components to it. There's the use case diagram, which is useful for basically enumerating them and showing the actors and the relationships. But it's really just a diagrammatic way of showing that. And you still need to create a specification that says what happens in that use case, what's the interaction. And then I'm going to answer a question in just a minute about branch method and statement coverage that just came in. So if somebody says, create a use case model for a particular set of requirements, you would show a use case diagram, which shows, you know, the use case in an oval, the actors and the system boundary. And then for each use case, you would write out the name of the use case, and then the primary path description, and any exceptions that might be involved. And so that combination gives you enough detail to create the actual description of it. And then later on, when we're doing our design work, we're going to break that into interaction diagrams to actually figure out which objects have to do what within that. And that's where we start to say, okay, we've got these high-level objects that basically come out of the domain. Now, how am I actually going to build them? And that was the discussion we started today. So let me just jump back to answer this question about branch method and statement coverage. So if I have a object, and I'm just going to start with a single object, in order to test it, one, I have to create a new instance of it. And typically we do this within a test scaffold. And that test scaffold, one, creates the new instance of the object, supplies any initial data, makes sure that any stubs that go along with the test are necessary. That's part of the test plan, right? What stubs would I need in order for this object to test? Because is there any collaborators that this object needs? Hopefully, if it's designed pretty well, there's not too much coupling going on. And then any test data. So within that object, we need to, one, test all of the methods. So that's method coverage. Have I covered all the methods that this object has? Including, as we mentioned in class, making sure that we test the even the most basic ones like get and set, because that's where very often a lot of things go wrong. So we're testing all of the possible methods, and then within each method you have branch and statement coverage. So you can see that those sort of go together, right? That we want to make sure that we cover all the statements in a particular system, but we also want to make sure that we forced all the different branches, and that will help us cover all the possible statements as well. Especially in a contemporary language like Java, pretty much if you test all the branches, you're also going to test all the statements. And we can do that by looking at each of the conditional statements that would cause branching, including while loops. Now, the example I gave in class only involved if-then-else's, but basically a while or a for loop is simply a compound statement that says, if my counter is still equal to 0, or, greater than 0, or whatever the condition is, and that's true, then I will execute this statement and then change the counter and just continue through the loop. So it's basically just an if then else as well. I have to come up with the appropriate data that will force that. And you'll recall in the example that we had last week in, I believe it was on Wednesday. I'm just going to pull open those slides for a second. We talked about, we talked about that code where we showed that you could take a compound if statement and break it down into simple statements to make sure that all of our test data forced each of the different branches. And we saw right away that what happens is, especially with multiple if statements, we have to go through a lot of combinations of data to make sure that we force all of the different branches, each one of them. And so it's worth taking a look at last week's slides on testing to see that example where we took the compound if and broke it down into simple ifs in order to do that, to make sure that we had all the possible statements. So when we calculated the cyclomatic number, the purpose of that was to see how many different branches we were going to have to wind up with. Now, it didn't tell us what the data was that would force those, but we knew that there would be a certain number of paths that we had to test. And that basically gave us our statement coverage. Then for our branching coverage, we had to make sure that we had reasonable test data that would force each of those branches. So you can sort of see how those are connected, right? In order to get all the statements covered, I have to take all the branches. In order to do all the branches, I have to make sure that my test data is appropriate for that. I hope that that answered that question. Trying to think if there's anything else. Oh, as I mentioned in class today, the way the test is going to work is, for about half the questions, there's going to be a problem statement. It's about 1.5 pages long. It doesn't take that long to read. That is going to give sort of a sample set of requirements. And from that, we're going to answer some questions about requirements for it, use case models, some tests, some boundary value conditions, the stuff that we've talked about in each of these. One of the questions that just came in is, what are some examples of units of functionality in iteration plans? And in your iteration plan, what we're going to do, typically especially when we're doing relatively agile development, what we'd like to do is to be able to say, for each of these iterations, I'm going to introduce a new unit of functionality. In other words, something that I didn't have before. And in most agile methods, for example, if we're compressing it into that, we may say that that's a story. We're saying we can implement this story, and at the end of this, we now have this ability to do something that we couldn't do before, or we can do it in a slightly different way. Some examples from our project that we're working on is, I may be able to do, I may, for a series of iterations, I may first be able to do the basic enable and disable of our channels. That might be a basic unit of functionality. Then I might go in and say, you know what, I can enter a racer number and they can start and finish. That's another interesting unit of functionality, because it doesn't make much sense to be able to start a race and not finish it. So that's when we start to look at that command as an object thing, and the command is sort of the use case as an object, sorry, where we start to think of that as, oh yeah, it knows how to start and finish up a race. Another unit of functionality might be that I can print out the results of a race. Another one might be that I can start a new run. So each of those are incremental units of functional ability in the system that typically are going to match functional requirements in your system. Now, depending on how those functional requirements were written, you may have a whole bunch of them, and you go through and say, you organized your use cases, and then from that, you say, okay, here are the really key ones that I want to do because I know these are going to force me to look at some of the hard parts of the system. And then I'll add on to that. Or it may be that you do some basic stuff and then you work with the customer on a very iterative basis, which would be a true agile method, where you say, okay, I've got the basic part in, now let's start adding on features as you see the system. And that's going to be a highly agile method for doing this. And now that works in certain situations, but it's hard if you have a lot of heavy-duty hardware that goes with the system, or you have really complex interactions with other systems. For example, if I'm doing a flight management and control system, FMCSs, that's not going to work out so well. You know, you don't go out each day and say, well, now that we can, you know, turn the engines on, what else do you want to be able to do? You might have a much broader plan, and you break it down into a series of iterations where you introduce functionality along the way, but you already know a lot of the requirements. What usually doesn't work well is you have all the requirements, then you do a whole bunch of design, then you do a whole bunch of coding, and then you throw it all together and see if it works. What you really want to do is you say, okay, I've got a good lay of the land. I've done all of my use case models. I've verified with the customer that those are pretty accurate. And now I start to think about all the object interactions, and I look at it and I go, you know, these key objects show up all over the place. I know that they're going to be great candidates for including in my early releases. Not surprisingly, they tend to show up, they're sort of the core elements of the system, right? For example, in our race timing system, we have system clock, the timer itself, we have channels, and we have sensors. Those are sort of the key elements in the system. And we're going to look at basic mechanisms, in other words, basic object interactions, and we're going to try and do those early and test those often along the way. So each iteration introduces some additional functionality, and it builds on these mechanisms that already exist. It has two advantages. One, if something goes wrong with those basic mechanisms, I can fix it. I've got extra time. The second thing is they are continually tested over and over, because each time I add new functional behavior to the system, I'm doing regression testing on the existing system, and that always helps me just in case I hadn't tested something before, or if adding in that new functional behavior can cause the existing system to suddenly exercise certain aspects of it that weren't being exercised before. For example, a new test case might be introduced that forced objects to behave in a different way than we'd expected before. I hope that answered that question. We did the branch, and then we did the use case model. Let's see. Oh, in requirements modeling, people had asked before the difference between functional and non-functional. Now, sometimes there's going to be where it's sort of functional, sort of not. In the test, it'll make, it'll be pretty clear which it is. For example, if I say that a withdrawal has to be completed within 3 seconds, is that a functional requirement? That is a performance requirement, but it doesn't tell me anything about the functional requirement for the withdrawal itself. A withdrawal would say somebody identifies themselves, identifies the account that they want, authorizes themselves, requests the money, the system gives them the money, and they take the money and get a receipt. That would be a functional specification. If I said that that a log has to be maintained of each operation, that's kind of a functional, non-functional thing. In other words, it's not functional behavior, from a user's perspective, but it certainly is functional behavior from somebody who's trying to debug the system. And so usually what you're going to see is that you'll see a use case that says, oh, I need to be able to examine the system log. You know, in other words, a more detailed one, probably not the top of your list, but nonetheless, it would still be a functional requirement. I think that's about it. For the patterns, there's 3 things you need to know. And so for the people who have joined us tonight, this will be worthwhile. 1, you need to know what the definition of a pattern is, and that is, it is a solution to a problem in a context. That's all you need to know. In fact, if you take anything away from all this discussion on design, that's all you really need to know. And patterns are an example of reuse within our system. We're going to talk about a bunch of different kinds of reuse over the next 3 weeks, but it is a way of reusing what we know, what are known to be good patterns of solution to problems. And so we looked at 3 of them. We looked at observer, which is an important one that says, if I have an object and there are a number of other objects that are interested in knowing when that object changes, the observer pattern is a good way of doing that. And it keeps a list of all of those objects which are observing it, and should the state of the observed object change, it will notify all of the observers of that object. That's a basic pattern, and we're going to see that it's very important in the model view controller pattern. The other one we saw was the memento pattern. It's a way of keeping information about an object so that it can be reinstantiated later on, and that's going to lead into our discussion on persistency. And then we saw the command as a pattern, and basically that is sort of a subset of making a use case into an object. We said we can take a command, which is basically a use case, and turn it into an object, into a class of objects. And the command pattern says, I'm going to break this into several parts. The command says, I have a bunch of different types of commands, but they all have the same interface, which is they can be executed. And that is, if I create an instance of a command, I can send it the message execute. And when I send it execute, it will do its very specific behavior, even though it has the identical interface execute. And it's also loosely coupled usually to its target, which is in the case that we saw today with the cut, copy, paste commands. We saw that anything that responds to cut, copy, paste can be connected to that cut, copy, paste commands. So they could be video, audio, text, graphics, almost anything. And so as long as those nicely, loosely coupled interfaces work together, we had that very nice system where the tool itself would create an instance of a command, execute it, then keep it on a stack, and we were able to keep an instance of that command. And then we could say, you know what, command, you're the perfect object for knowing how to undo it, because you just did whatever you're going to do. You know how to reverse that behavior out. It might not be simply restoring the state. It's usually more complicated than that. You have to get it back to where it was before, and that may involve some activity. But if I cut something out, I knew where it was cut from, I knew what was cut out, and I knew what the target was. So if you tell me to undo it, I can go back to the target, open it up at that spot, and reinsert what had been cut out, and I'm back to my original state. And that allowed me to, for example, keep a stack of commands. As I execute them, I could always work my way back down the stack to undo them until I got to the end of the stack. It gave me a log trail of everything that I did, an audit trail. Here's all the commands. And you start to see that those commands actually look a lot like transactions, which we're going to see much later on in the class when we talk about processes and persistency. Not much later, but several weeks from now. So if you go through that study guide, you should do pretty well. One once again, key things, knowing the elements of the software development process, which we did in the quiz, knowing class, object, and interaction diagrams, which we did in the quiz, knowing use case models well and use case descriptions, difference between functional and non-functional, the two types of testing that we talked about, white box and black box, and then the difference between test plans and test cases. That's important. Test plans organize test cases. Test plans tell me, what do I have to gather up? Who do I have to gather up? When am I going to do it? And what's the purpose? What am I actually trying to test? The test cases are, oh, if I'm going to try and test to make sure that my withdrawals work, here's a bunch of the test cases. And then boundary value analysis, always very important. The cyclomatic number, always a good thing to know, because that's going to give me an idea of how complicated this is going to be. Then the coverage, and those 3 patterns, and you should be good to go. So it's just 50 minutes long. I think it's usually, it'll be about 16 questions. So you should be able to do pretty well with that. If there aren't any other questions, I'm going to let you get back to your other work. If there are any other questions, you can text me at 414-899-8269 or email me, and I'll be happy to answer those. If not, we're going to do this again tomorrow night at 9 o'clock for those where it worked out better at 9, and I'll also have those other tools set up properly. This is the first time I've done a Google Hangout broadcast, and it works a little different than a regular Google Hangout. So, so we'll do that. In fact, what I think I'll probably do is just do a regular Hangout tomorrow, and that way it'll make it a little bit easier. Great. Well, have a good evening, and if you're not out tomorrow night, we'll see you at the test on Wednesday.